So we have two vectors. Vector u is negative 31, and vector v is negative 1, negative 2. It's asking you to express vector u as the sum of vectors p and n, where vector p is parallel to vector v, and vector n is orthogonal to vector v.
Okay. Okay. This is another thing that we'll use quite a bit towards the end of the semester. It will be at least important to understand at the end of the semester. Here's the basic idea. We've got these two vectors. I'm just going to draw one of them like it's going in the horizontal direction. They could be pointing in any direction. And I know the angle, or I'm sorry, I don't actually know the angle between them here. If I knew the angle between them, this would be a little easier, but I don't know it. And what I'm asked to find is a vector that goes this way, parallel to v, and then a vector that goes orthogonal to it, that add up to u. And if v was pointing in the horizontal direction, then this would just be finding the horizontal component and the vertical component. But you can see v is not just pointing in the horizontal direction. So this is not just a straightforward take the x component plus the y component. What ideas do you have about how we can get our hands on one of these vectors?
Well, vector p is parallel to vector v, so we know that vector p is simply it's a scalar multiple of vector v.
Okay, good.
And then for vector n, it's orthogonal, it's perpendicular to vector v. So we know that we take the dot product of n and v.
Mm-hmm.
You get, you get 0.
Okay, good. So we know that p is a scalar multiple of v. We know that n is orthogonal, so the dot product of n with v or n with p is 0. Good, that's what we know. So let's start with p then. If that's a scalar multiple of v, can I find the scalar multiple of v? Because, yeah, let's just say that. Can I find the scalar multiple? Like the number that I would need to multiply v by to get p? How can I find that? What could move us in that direction?
No, I just set it up to where if it's just a scalar multiple,
Mm-hmm.
I use like a variable x,
Mm-hmm.
as a scalar value. So then
Okay,
p is equal to x times vector v.
good.
And then you also know that vector n is orthogonal to v. So therefore, you know that n times the dot product of v equals 0.
Okay, good.
And that's as far as I got, unfortunately.
Okay, this is good. I want to know, how can we get this x?
I just use the formula for, so I just use the vector v, second vector v, using the formula,
Okay,
and then over magnitude vector v times regular vector v again,
okay,
and then times that inside there with the vector v.
okay. So you're claiming that this is the x that we need right here? Okay, good. That is the x that we need, and you can If you have this formula memorized, then you can use that for sure. But I want to know why is this the specific number that we need? It definitely takes some work to get from here to here. And you don't have to show that work if you have this memorized, it's no problem. But there is once you think through this a couple of times, you can get it without memorizing this. Here's the main idea that I want to propose to you. Take the vector v and scale it down to a unit vector that points in the same direction as v. So if I take v and I scale it down to a unit vector, then how can I represent that? That's v times, and then how am I scaling it? To turn it into a unit vector.
By magnitude.
Like
divide by magnitude.
Yeah, good. Divide by the magnitude. So one way I can write that is, I'm going to multiply this by 1 over the length of v. So I take v, I scale it by the length of v, that shrinks it down to a length of 1. But it still points in the same direction. Or, if v happened to have a length shorter than 1, then when you do this, it actually scales it out to have a length 1. Once I have it as a length 1, then how can I find the length p? How can I scale it out to make sure that it's exactly p? Well, one way that we could say it is you take this unit vector and you just multiply by the length of p, right? If we knew what the length of p was, then if I multiply that times this unit vector, that definitely gives me p. Because it's pointing in the correct direction and it has the correct length. So it is p. Now the question is, what is the length of p? How can I get that here? I'm not given p. I'm just told that p is parallel to v. And so this is where the work comes in, going from x to this expression. So you can see this 1 over length of v is showing up here. And the length of p is going to give us the rest of this stuff. So first, we've calculated this a few times today. How would I find the length of p here if I knew this angle theta?
U cosine theta.
Say it again.
U cosine theta.
Okay. Length of u cosine theta. Good. This is just like the force problems that we did earlier. Cosine theta is length of p over length u. So you get this. Now, we can update this equation. The length of p looks like this. So we have length of u times cosine theta over length of v is the scalar that we want out in front of here. The problem with this, though, is that I don't know what theta is. Theta is actually not given to me, right? But this looks really close to our definition of dot product. What do I need to do to this to actually turn it into the dot product?
Rearrange it.
Okay.
Rearrange the dot product to fit the equation better.
Okay, good. So you can take the dot product equation and solve for u cosine theta and plug it in right here. Let's go ahead and do that. What's the dot product equation? Do you guys remember?
Dot product of u times square root of v equals a magnitude of u magnitude of v cosine theta.
Okay, good. That's right. And we want to solve for length of u times cosine theta here. So divide both sides by length of v. And now, if I plug this in for this, then in the denominator I get 2 length of v's, and that's where this is coming from. And in the numerator I have length u times length v. So just plug this in for this, and you get the correct scalar. Another way to think about it is that I know that the dot product looks like this, so I'm just going to multiply the top and the bottom here by length of v, so that now this numerator is the dot product, and the denominator turns into whatever it is. By the way, if you take the length of v times the length of v, that's the same thing as the dot product of v with itself. So another way to write this is u dot v over v dot v. Because remember, the length of v is the square root of like v1 squared plus v2 squared. And v dot v is -1 squared plus -2 squared. So when you do length v times length v, the square root goes away, it's just v dot v. So we're almost there. I took a long time to explain where p is coming from. I think it's helpful to actually think through it so that later, if you happen to not memorize the formula exactly right, you can just think through it for a couple of minutes and pop it out yourself. U dot v is -3 times -1 gives me 3, plus 1 times -2 is -2, and then v dot v is just this -1 squared plus -2 squared, so 1 plus 4. This was v. So that's one way to write p. Once I have p, it's actually pretty easy to get n. What can I do to get n? Yeah, good. I can just take this equation right here. If I want to get n, just subtract p from both sides. So u minus p will give me that n. And then one of the things that John mentioned was that this dot product should be 0. So once I do the subtraction, I can just check my answer real quick by taking the dot product, making sure I get 0. So if I take u minus p, I've got -3 minus a -1/5, so it's +1/5. And then 1 minus a -2/5 +2/5. And then this is -15/5 and 5/5. So if we're asked to rewrite u as p plus n, where these properties are satisfied, then it looks like this. I'm going to go ahead and pull out 7/5 here. So this was my p. P, this is my N. And if I look at the dot product, I can see it's going to give me 2 minus 2 if I ignore the scales out in front.